And so what I want to do is, there is another set of notes. It's titled Surface Modified and Polymer Modified Electrodes, and I want to spend some time talking about those electrodes. And the idea here is, in the previous set of discussions, we talked about the effect of molecules being absorbed on the surface or ions being absorbed on the surface, either naturally because of the electrode potential and then so on. In this particular section, we're going to talk about actually the where people have intentionally put either absorbed molecules on the surface or a polymer modified surface where they've attached a polymer to the surface for specific chemical reasons, and we're going to talk about the advantages you might have when you do these sorts of experiments. And so basically the idea is, let me put a molecule on the surface or a polymer on the surface, and why would I do that? Well, I want to somehow modify the properties of that electrode. For example, we had a talk in the chemistry department a few weeks ago about a guy doing semiconductor electrochemistry. And was that here? Yeah. No, I was thinking at PigCon. I was at PigCon. I was hoping it wasn't there. But yeah, he was talking about semiconductor electrochemistry. He's talking about corrosion of the semiconductor under certain conditions. And one of the things people might do is put a polymer on top of the semiconductor material to prevent the corrosion from occurring. Or it actually turns out that there's now a product that uses a conducting polymer material that's put on stainless steel or ion electrodes to reduce corrosion effects. The other thing we can do is to use this modifier to pre-concentrate electroactive species to increase the sensitivity of a reaction, or if we pre-concentrate materials at the electrode surface, we can do increased efficiency of a reaction. People have tried to use this to promote chiral electrochemistry. In other words, put a chiral modifier on the surface and then try to do chiral-based electrochemistry to do electrochemical transformations that would preserve stereo-specific properties. That hasn't really worked that well, actually. The other thing that's important also is electrocatalysis. Try to promote a reaction that would not normally be occurring at the normal electrode surface. Try to speed up a desired reaction by adding a catalyst to the surface. A catalyst would be a normal catalyst, or it might be an enzymatic catalyst, and that's a very popular process. So catalyst, for example, or instead of having a direct oxidation reduction process, we can take and convert using this oxidized molecule to promote a reaction, for example, of A to B that would not normally be directly accessible by electrochemistry, but by using the oxidized reduction process as a catalyst, we can promote A to B, and that's an important industrial type idea, and also is important for certain types of analytical applications. The other thing we're going to do with electrochemistry of modified surfaces, a lot of times people are interested in understanding the electrode surface as a surrogate for biological membranes, and so people will talk about biomimetic surfaces. In other words, they're going to try to mimic the processes of biological membranes with an electrode modification. So by putting a polymer in there, you can see what happens how is charge transport affected by the reaction on the surface, and this is something that's important in biochemistry. The other thing that people are interested in is what happens when we try to get charge transport over large distances. And so what you can do is put in a layer of material. If you do it in a very careful way, you can put a layer of material that acts as a spacer between the electrode and the electrode material that you're trying to do electron transfer to. And that spacer then acts as a test for theories of electron transfer rates. Because in principle, you should be able to theoretically derive what the rate constant is for something that's a certain distance away from the electrode. And by varying that spacer, you can make that happen experimentally. Now, in pretty much all of these intentionally surface modified and polymer modified, you're going to get surface type waves. You're not going to get diffusion waves. So you're going to look at waves that are, you know, these surface waves. That's not a very good one. Let's try that again. Where you get basically zero peak separation, or you're going to look at waves that have non-zero peak separations and use those to derive rate constants. Let's first of all, in this process of talking about this, talk about actually modifying surfaces. What actually are you going to do to modify a surface? How can you do it? How can you change the properties of an electrode surface? So how is the question? How to modify a surface? Well, you can do it lots of different ways. People have come up now with all kinds of different ways. One is you can do a covalent bonding. And this is still a very popular idea. The idea is that you can take the carbon or metal surface and directly attach a molecule or some other species to it by doing a chemical transformation to form a covalent bond between that molecule and the surface. And you can use a metal oxide surface as a starting point, or a carbon surface, or a carbon oxide. The advantage of the covalent bonding is that when you've attached something with this covalent linkage, it's very stable. It's not going to come off unless you polish it off or you do some very dramatic electrode reaction. And it's stable usually in the presence of electron transfer because that bond is not usually electroactive. You can't reduce or oxidize that bond directly. The other idea is you can use chemisorption, where you have a very strong chemical adsorption energy, and that can lead to chemisorption. For example, this Hubbard study where they put this allylamines on the surface, there's a chemisorption process there. It's not covalently bonded. There's just a very strong electrode adsorber interaction that makes it somewhat irreversible adsorption, but it's not completely irreversible, so these chemisorbed surfaces are not completely stable. So there is a stability problem. But it's one of the earliest processes. The third thing is film deposition. And the idea here is that you put on a material in a very thin film, but it's stable because the film holds itself together, and it's difficult. You'd have to remove the entire film to get the material to come off. So for example, you could put a polymer on, and you could either do a sort of an electrodeposition where when you oxidize a monomer, it forms, polymerizes, and it polymerizes to form this insoluble polymer right at the electrode surface. And then that just stays on the electrode surface. It doesn't remove off because it's too big to diffuse away from the surface at that point. So polymers are a very popular one, or you could dry a solvent-based polymer onto the electrode surface. That's a popular way too. Also, some clay materials can be used as modifying films. Some aluminosilicate clays can be made as films on the electrode surface, and they actually are very useful in some certain circumstances. The other way to put films on the surface, especially as monolayers or multi-layers, where you have a very well-defined arrangement of molecules. The problem with polymers and clays is that you really don't have a very well-defined thing. You can have a very well-defined thickness and a well-defined composition, but you don't have a well-defined arrangement of molecules. In other words, you don't know if the molecules are all arranged next to the surface or not. they're randomly oriented generally in polymers and clays. But you can put molecules or ions in multi-layers as Langmuir-Blodgett layers called LB films. And now very popular are so-called self-assembled films. Or monolayers, often they're called, because you're using them, often they're monolayers, they're often called SAMs, for self-assembled monolayers. So if you see that, that's what we're talking about. Let's talk about the covalent bonding first, and then we'll talk about these other ideas. Good reference for this process, they're a little bit old now, but they're still pretty current. There's some of this newer stuff isn't in there, but Royce Murray at the University of North Carolina has done a lot of this work. And he has published things in the Accounts of Chemical Research. That's a good one. Accounts of Chemical Research is often useful to read because it's written more for the general scientist rather than for the electrochemistry specialist. And so for people starting out, you might find that very useful. Also a very heavy-duty volume in this series edited by Bard called Electroanalytical Chemistry, volume 13, 1984, pages 191 to 368. And I would recommend those if you're interested in monolayers on surfaces. And I'll just illustrate a few of the techniques. First of all, on metal oxide surfaces, you get often this MOH structure. And for example, it's not really a metal oxide in this case, but a silane would be an example of an atom oxide or hydroxide surface. And you can often get tin oxides, ruthenium oxides. Platinum has a platinum oxide phase that's somewhat stable. Aluminum has an aluminum oxide phase that's quite stable. So all these surfaces have oxide phases. And if you have, for example, this sort of behavior, you can use methoxychloro. Oops. Let's try that again. Methoxychlorosilane, for example, would be one example. X could be a halogen or some sort. And then that reaction is, the surface energy is enough so that you get a direct attachment there. And you may get direct attachment to one oxygen, or you may need two oxygens to the attraction. But you'd get a silicon and then an R group attached. And then depending on what R is, maybe that's the final result, or maybe R is some precursor to another chemical reaction that you do. So you could maybe do some additional organic chemistry on R to do this desired electrode surface reaction. I won't go through all the things because there's not really that interesting, and you can see it in the book. For example, though, once you've put stuff on there, you can put in a material like this, which is a amine-containing group, and then you can attach to that with an amide bond this sort of thing, where you've got then a long chain alkyl group attached to then a ferrocene molecule. I don't know if we've talked about ferrocene yet, but ferrocene is an iron cyclopentadienyl complex. It's very common in electrochemistry, and especially in organometallic type electrochemistry. Very easy to make, but it's a very easy to oxidize chemical species. So now you've got this oxidizable chemical species on the end of a pretty long chain. You can see there's 15 carbons between here and here, and then there's some additional spacer here. So that's well separated from the electrode surface. But if you do a reaction of this, you get nearly reversible electron transfer. The only thing is you see a slight shift away from reversibility, although it's pretty close to reversible. And what you're seeing there is this long chain cyclopentanediol group is in the reduced form here, and then you'd form it on this side, you'd form the oxidized form of it. Which is the ferrocinium of that, the ferrocinium. So you're doing the scan in this direction because it's an oxidation. So you oxidize that and you reduce it back to the original state. Now, obviously the electron is not going to be, this could be several tens of nanometers at this point. So the electron can't really be transferred over that entire region through space. It's not very likely to get an electron transfer that way. What's happening in this particular case is that this chain is flexible enough so that the cyclopentanediol end can actually wrap itself around and become close to the electrode surface often enough so that electron transfer can occur from the electrode to that end group and then get a reversible electron transfer process. Now, if this was a rigid rod holding this far away, you would not see probably any electrochemistry whatsoever, because the electron would have to go all that whole distance out and back, and that would not be very likely. It would be very slow reaction, electron transfer process. How are we doing on time? Why don't we stop here for a second?